Worksheet 7 uses Hess's law to combine reactions that have known enthalpy changes, like these ones down here, as the givens. So we're going to combine them in a way where it ends up matching the target reaction, which has an unknown enthalpy. So in this case, the first reaction we're dealing with, nitrogen is in the reactant side on both the target and the given, so that's probably the right spot for this one. Down here in reaction B, we're trying to match nitrogen dioxide, and in this case, the nitrogen dioxide is in the reactant side, but it needs to be in the product side. So, in order to make the given reaction B match the target reaction, you can switch the direction of this reaction. So we're just going to write this the other way. So 2 nitrogen monoxides plus an oxygen molecule can yield 2 nitrogen dioxides. Now if you switch the direction of a reaction, the impact that has on the enthalpy change is that it just switches the sign. So taking nitrogen monoxide plus oxygen to produce 2 nitrogen dioxides, instead of a plus 112, it becomes a minus 112. And now we have the 2 nitrogen dioxides matching the target reaction. And from here, nothing else seems to need to be changed, so you can just begin combining the reactions together. So in this case, you have nitrogen on the left, which we already indicated this nitrogen matches this nitrogen. On the left, you have 1 oxygen. I'm going to use a different color. You have 1 oxygen here, and you have 1 oxygen here for a total of 2 oxygens on the reactant sides. This chemical, nitrogen monoxide, is not anywhere in the target reaction at all. So nitrogen monoxide here actually will cancel out with the nitrogen monoxide down here. So there's 2 in this reaction on the product side, and in this one, reaction B, there are 2 on the reactant side. So it's like having the same thing on both sides of an equation. They end up canceling out. So the only chemical remaining that we haven't indicated is the 2 nitrogen dioxides. So because all of the chemicals from these givens match the chemicals in the target, you can take the 2 enthalpies and add them together. And if you did this on a calculator, 180 plus a negative 112 would give you 68. So the enthalpy change for this reaction would be 68 kilojoules. The second question is the same process. So you have a target reaction. So up here is your target. And you have 2 givens where you are trying to match what the reactants in the givens are to the products. So in given reaction A, the chemical that we have is carbon monoxide to match the target. But there's 2 problems. There are 2 of them, and it's in the product side, whereas in the target, there's only 1, and it's in the reactant side. So the change we need to make to reaction A is that we need to switch the direction. So I'm going to use a negative sign because that's going to change this into the positive. And we need to cut it in half. So when you rewrite this equation, you're going to end up with carbon monoxide yields carbon plus 1/2 a mole of oxygen. And so that changes the enthalpy to be a positive number, and we only need half of that enthalpy change. So that's plus 110.5. In reaction B, the chemical that we need is methanol. So this chemical up here is methanol. And it is on the right side of the reaction, but the only problem is that it is twice as much as we need. So we're going to multiply this one by half also. So the sign stays the same because we don't change the direction, but it is negative 201.2 kilojoules. So if we rewrite this equation, we have now carbon plus 1/2 a mole of oxygen plus 2 moles of hydrogen. That makes 1 methanol. So now we can look at the reaction that we're trying to get. So in the target reaction, we have carbon monoxide, and that's good on the left side. On the target reaction, we have 2 hydrogens in the reactant side, and right here we have our 2 hydrogens in the reactant side. Our product needs to be methanol, and here it is. Methanol is the product. So the only things that are left over are this carbon is available in the given reaction B on the reactant side. But this carbon is in given reaction A, but it is on the product side. So because these are on different sides of the arrows, they are able to be canceled out. And there's only one, so their numbers match. The other thing that's able to cancel is because you have half a mole of oxygen in the product of reaction A, and we have half a mole of oxygen in the reactants of reaction B. Those ones end up canceling out, so that there are no other chemicals left over besides the ones that we're trying to match to the target. So carbon monoxide is here. Hydrogen is here. Methanol is here. So, because we have crossed off all of the chemicals that are not involved, we now can take the sum of the 2 enthalpy changes. And if you take 110.5 and subtract 201.2, you end up with negative 90.7. So that would be the entire enthalpy change. The third example uses 3 reactions to help us get to a target enthalpy, which is possible. We can do that. And we'll start by just looking for chemicals in the target reaction that match the chemicals in the givens. So it's often easiest if you start with chemicals that are kind of unique. And in this case, the carbon disulfide liquid definitely it only appears in target reaction, in given reaction C. So the carbon disulfide is here, and the problem with the carbon disulfide is that it is in the products when it needs to be in the reactants. So that changes this. Carbon disulfide is going to turn into carbon plus 2s. But now that enthalpy change is going to be exothermic. So the change for that has to fit there. The next chemical that we're going to look for, oxygen occurs in several spots. It's here, it is here, and here. So it might be a good idea to wait until we get to the end for that one. So instead, we'll look at carbon dioxide. So carbon dioxide only appears in one of the reactions, and it's actually right here. So it's both in the product side, and it has the right number. So we don't need to do anything to this first given reaction. The last chemical from the target reaction is sulfur dioxide. Now there are 2 of them. Here the sulfur dioxide is in the products like it needs to be, but because there's only one, we're going to double this entire reaction, and we're going to double the enthalpy change. So that means we have 2 sulfurs plus 2 moles of oxygen that will produce 2 moles of sulfur dioxide. And then when you double this, it produces a new enthalpy change of negative 593.6. So now we can go back and double check our oxygen to see how this works. So if you need 3 oxygens in the target, and in the first reaction you have 1 oxygen, and in the second one you now have 2, you ended up with 3. So now that we have confirmed that each chemical that's in the target reaction is present in the right amounts and in the right sides of the given reactions, we can go around and cross off the chemicals that are not present at all. So in this example, reaction A, you have carbon, and reaction C has carbon. In reaction B, you have 2 sulfurs, and in reaction C, you have 2 sulfurs, and of course they are on opposite sides. So these 2 sulfurs are in the products, and these 2 sulfurs are on the reactant side. So the only chemicals then remaining after all of these canceling outs are the chemicals where we need them. So carbon dioxide is present on the reactant side. You have your 3 oxygens. Sorry. Carbon dioxide is present on the product side. You have your 3 oxygens, which are present on the reactant side. And you have your carbon disulfide on the reactant side, and we have our sulfur dioxide on the product side. So everything that needs to have been done to the chemicals has been done. And so when you add all of these enthalpies together, so the sum of these 3 enthalpies is negative 1075. So your answer is negative 1075 kilojoules. That's how you use Hess's law to combine the enthalpies of known reactions to determine the enthalpy of an unknown reaction.